We're going to look at uniform circular motion in the horizontal plane. So if you were swinging something parallel to a desk, not in a vertical or Y plane. According to Newton's second law, acceleration requires a net unbalanced force. Okay. So we talked about acceleration resulting in a change of velocity earlier. So they have this little example here that if an object is moving at some initial velocity and a force is applied to it in the same direction as its motion, the final velocity will simply be greater because we've applied the acceleration in the exact same direction as our velocity. Okay. Now, if we have this object moving with an initial velocity, but the force is applied at a slightly different angle, our speed will increase and our direction will change in this case. So we have to consider vectors here. So an increase in speed and a change in direction can also be acceleration. So note that. All right. Again, a change in speed or direction is considered an acceleration. So here we have like this picture of an object being swung in a horizontal circle. The mass is moving at a constant speed. So if this is taking a picture every 0.1 second, we can see that in the same time frame, they're moving the exact same distance each time. So it does not have a change in speed. It is a constant speed. Okay, but it is accelerating because it's changing direction. Okay, so initially, our object was moving, let's say, this way. Then over here, it's moving this way. And now it's moving this way. Here, it's moving this way. So because its direction is changing, it is having acceleration applied to it. Now, its direction is changing by the exact same amount, if you will, each time. Therefore, acceleration is constant. So we can say that a net force is perpendicular to its motion. Okay, so a net force that is perpendicular to the object's motion does not affect the speed. It only affects the direction. Okay, uniform circular motion involves an object in a circle at a constant speed. All right, this perpendicular force here is the one that we are going to discuss at length in this topic. All right. Uniform circular motion is accomplished by applying a force at 90 degrees to the original motion of the object. All right, so if a ball is attached to a string, the ball can be put into uniform circular motion by applying a constant tension force on the string. So we see that here. What is important to note is that the direction of the force towards the center of the circle, okay, this is called the centripetal force or a center-seeking force. So when things are spinning around in a circle, the force applied to them is the centripetal force, and it is pulling them towards the center. If the centripetal force is removed, the ball will continue to move at a constant velocity in a direction tangent to the point where the force was removed. What this means is if this ball is spinning around here and the string breaks at the very top, this ball will continue to move in a linear direction outwards this direction. Okay, so those are the important things to note to get ourselves started here. So where does centripetal force occur? There's a few different scenarios in a horizontal plane that we can look at. Okay, so objects do not just decide to exhibit uniform circular motion on their own. There must be a force causing circular motion. So, in other words, it says circular motion is the effect of an unbalanced centripetal force acting at 90 degrees to the velocity of an object. This unbalanced force is the cause of circular motion. So when an object is on a string or a rope put into circular motion, it is the tension in the string that is the centripetal force. So I like to just skip to gravitational force for the start here. So when anything orbits the Earth or planets are orbiting the sun, the centripetal force, the force that is keeping them in the circle or their orbit, let's assume they're all circular, is the gravitational attraction. So objects will orbit Earth because of Earth's gravity. Okay, so Earth's gravity is pulling them inward. Earth's gravity is the centripetal force in this case. So I like to think of gravity when I'm trying to remember that centripetal force is always pulling inwards. So gravity is the nicest example that we're very clear on. Again, gravity is attracting to the center of that mass. So to the center of Earth, everything is pulling towards it. Okay, so highlight that when satellites orbit the sun, the centripetal force is provided by the mutual attraction of gravity. Okay, so Fg is equal to Fc. Then I can apply this to other cases. So the tension force, let's go back to one here. When an object on a string or rope is put into circular motion, it is the tension in the string which provides the centripetal force. So if we are swinging an object around in a circle, we typically would have the force of tension. I don't know why it's like that. This is the centripetal force in this case. Okay, the tension in the string, which provides the centripetal force. Again, if the rope breaks, the object will continue to move in a straight line perpendicular to where that happened. When a car turns a corner, the friction of the road on the tires or the banking of the road provides the centripetal force. Okay, so friction is the centripetal force here. If friction is zero, aka we have icy conditions and we don't have friction, we will not continue in our circle and the car will continue to move in a straight line, obviously missing the curve. So again, coming back to gravitational force, that is the one that I think makes the most sense, and I can apply backwards to other scenarios from there, understanding that centripetal force is equal to a force that is pulling inwards on our circle. So just to kind of reiterate the direction of centripetal acceleration, there's this diagram in our notes. And again, some of our labels have disappeared here. So an object at point A here has a velocity of VI. Then it travels a very short time later. It's obviously traveling clockwise here. It gets to this point, and that will be our VF. Okay. These are equal in magnitude. So VI is equal to VF in terms of its numerical value. The only thing that's different is the direction. So a change in velocity is always VF minus VI here. So what they've done is they've taken their vectors. So they've taken VF and they've subtracted VI. So you can see that these are parallel to their original vectors here. VI's direction is simply changed because we are subtracting it here. So the difference in these two vectors here is the change in velocity. Okay, the change in velocity is pointing directly inwards to our radius here, and it is a change in direction. Okay, so note that the change in velocity is pointing towards the center of the circle. This means that the acceleration will also be directed towards the center of the circle. So this is, again, why it is called centripetal, the center-seeking acceleration. So AC is the subscript for it. So uniform circular motion and speed. When we are working with the speed of an object, its basic equation for circular motion is this. Now, this doesn't actually occur on your formula sheet, but we can quickly derive it. Okay, so on your formula sheet, we know that AC is equal to V squared over R. It's the last equation in our kinematics section. We also know that F net is equal to M times A. So if this becomes FC, this will be AC. So the centripetal force is equal to mass times V squared over R, which of course is mv squared over R. So it's not actually on your formula sheet, but it can be quickly derived. Okay, where we know mass has to be in kilograms, velocity is meters per second, and radius must be in meters to cancel with the unit of meters per second there. I totally thought that I had my blank examples here, so my apologies. I was going to work these out with you. Calculate the centripetal force acting on a 2.5 kilogram object while whirling at a speed of 3.5 meters per second in a horizontal circle of radius 0.8. Horizontal is key here. We are not working with vertical quite yet. Make sure you list your information. I think it's going to become important again here. Forces, we usually included a lot of our information in our free body diagram, but now we do want to make sure we have all of our variables. This time we were looking for FC, and so we can quickly use that formula we just derived, plugging in all of our information, and we get 38.3 newtons, which we should actually round to 38 newtons. So again, we did just use Newton's second law, where force equals mass times acceleration. We included our centripetal acceleration. What they've done here is, again, put it's equal to mass times acceleration. So mass times acceleration is equal to mass v squared over r. Masses cancel out. And again, this was where we started on our formula sheet. Okay, a car traveling at 20 meters per second, so V equals 20 meters per second, goes around an unbanked curve, which is important because otherwise we're going to have some angles to deal with here. An unbanked curve in the road which has a radius of 122 meters. What is the acceleration experienced by the car? So we're looking for AC. A quick sub in here and we get 3.27 meters per second squared. We should probably round this to, I changed that to 20 in my notes, but technically 2 sig figs here, 3.3 meters per second squared. Remember the force that is created, the centripetal acceleration is the friction force between the tires and the road here. Quite often we're given the period or frequency of rotation rather than the speed. So period is a large T. It's the time required for one circular rotation. So it's the time required to go around a circle once. Its unit is seconds. Frequency is the number of rotations or cycles in one particular unit of time. So in this case, we're usually doing hertz, and that is how many times it goes around in a circle in 1 second. So we can get to this formula here, which is also on your formula sheet. It's under waves, kind of next to our centripetal acceleration. So just using that formula, the frequency of rotation for an object is 4 hertz. What is its period of rotation? So 0.25 seconds when you do 1 over 4 hertz. So again, we have a constant velocity. So we can use our V average formula. We know that the distance around a circle is 2 pi r, which is the circumference. So we can put that in for the distance traveled and get V equals 2 pi r. And then the change in time is the time it took to rotate once, which is t. So, for example, if an object traveling in a circle with a radius of 5 meters has a frequency of 6 hertz, What is the speed of the object? That should look more like an R. So with F, we can calculate T. This is on your formula sheet. Sorry, it's the second last equation in kinematics. I would calculate T first rather than subbing it in, but you could say that V equals 2 pi R over 1 over F, which brings you to 2 pi RF. Doesn't matter whether you do T first and then sub in or combine all of those equations. Either way, plugging in what we know, we get 188.5 meters per second. I changed my notes to have an extra decimal here and here so that I could keep 3 significant digits. We should round this. I think it was a 0.4 rounded to a 0.5. I got 188 meters per second, but 189 meters per second would work as well. Again, the significant digits are all over the map here. Okay, a very useful version of centripetal force can be formed by substituting this into Fc equals mv squared over r. So Fc equals 4 pi squared mr over t squared. Now again, this isn't directly on your formula sheet. However, we do know that F equals mass times acceleration. It does say that, AC is equal to 4 pi squared r over t squared. Combining these, we get F equals m times acceleration. So 4 pi squared r over t squared. We usually put constants out front. So that's how the 4 pi squared got out front. R over t squared. This is not on your formula sheet, but could be derived. Okay, so let's put that into use. If the centripetal acceleration on a stone being whirled in a circle at the end of a 1.7 meter string is 350 meters per second squared, what is the frequency of rotation? So we have the radius, which was 1.75 meters. The acceleration it is experiencing is 350 meters per second squared, and we are being asked for the frequency. So what I did is we can use this formula in our formula sheet of AC. And we're going to solve for t squared. Again, because if I can find t, I can quickly find f using this formula, slightly rearranged from our formula sheet. So going backwards, finding the period of rotation, t equals 0.444 seconds. Putting that into our frequency calculation, we get 2.25 hertz. A 1,000 kilogram car enters an unbanked curve of 80 meters in radius. If the coefficient of friction between the pavement and the car tires is 0.51, what is the maximum speed which the car can go around the curve? See, what we know is an unbanked curve, or in a curve, Fc is equal to the force of friction. So if I can find Fc, I can find the force of friction. So we know that the force of friction is mu times Fn. Now, I can find Fg, which in this case is also equal to Fn. Again, with absolute value because their directions are opposite in our free body diagram. So finding this, Fn is equal to the absolute value of m times g, and we get that Fn is 9,810. So finding the force of friction using that, we get the force of friction is 5,003 newtons. Because we now have the force of friction, we know that it is equal to the centripetal force. We can sub into our equation here and find that velocity is 20 meters per second, should be 20 with our 2 significant digits from the coefficient of friction. All right, that looks to be it. Take a look at those practice questions in your work booklet to get some good practice with this before we move into uniform circular motion in a vertical direction.